So I guess we can slowly start. I guess it has been a week because National Day holiday, just still one day from our class. So we have been not seeing each other for 1 week. So hopefully you still have some idea what has been covering, but uh we'll review from scratch and then go ahead and at least we should be able to get to finish the discrete random variable, and hopefully we have some initial discussion on the continuous random variable. So let's start on the reviewing what is random variable first, because I guess that is the first order of business. The first thing to say, random variable is the way to assign number to outcomes, right? And that means that we are trying to measure the outcomes in the sense that the number to be assigned it should be meaningful. Okay, of course you can do categorical or nominal, but they would not be too meaningful for the usage. Okay, and what kind of number you can put in is called the support, right? And in our class, we distinguish discrete and continuous because we focus on numeric, right? Of data. And in this case, how we assign is through the number of head and tail, right? You can see the random variable is simply mapping the outcome of head to 1 and tail to 0. And you've told the con twice, then you have head, head, tail, 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 head. Then we would have this type of results. And after that, we also look at continuous, which essentially is using decimum numbers, right, in our applications. So just to a gentle reminder why we have to distinguish the two is because the discrete is you can use the standard math you learn in high school, where continuous require calculus. Okay, so that is the fundamental difference. And for discrete random variable, the way we describe is the probability mass function. Okay, and that being said is saying that you give me the possible values of the random variable, the values of random variable, and I give you the probability, right? So this P, the big P, is the full description of the random variable. Okay, and this example I've been shown it. I'm not going to repeat it. So the big F would be the cumulative one, the CDF, is going to be saying that if you give me the number, I give you the probability less than or equal to the number you give me. That essentially graphically means if you have the left-hand side, the P, you will see the right-hand side F by stacking the P. And if unstack F, you get the P. So they are the same thing, but you look at different perspectives. And the same goes if you toast the gun twice, and it's not uniform, but the idea is still the same, right? You're stacking towards the from P to F. And after that, we know we study expectation and variance. The reason why we do this is because big P and big F can be very complicated. So in order to make the case that, okay, I don't want to know the P, I don't want to know the F, but rather, can you give me a number that summarizes the P, right? Or F is the mean. This is the way you learn in the first class of this course, right? We say that in order to have a number that summarize the data, use the mean. right? Or variance, mean or median or mode, right? It's mean here. And expectation is a number that summarize the P, okay? And we also talk about uh, how this expectation works, okay? This is going to be following this. And indeed, actually the same hold true for the mean itself, right? If your data is not random variable, but rather some random data as a number, right? And you also follow this type of property of the mean. Okay. And we have another measure, right? It's variance. It's telling us how good is our mean. And the variance is looking at the square distance weighted by probability, right? So this is the formula here. And we learned that the property of the variance is not the same as the mean. It's not linear. It's quadratic, right? And I'm not going to go into great detail for each formula, but you would know it, right? In particular, the second equation essentially said if you have the variance of a random variable plus the constant, it is you can discard the constant term. And in application in finance and investment class, you know that the risk is a measure of variance, right? So the variance of a portfolio with stock and cash will be same as the risk of the stock because cash has no risk. And we also have the idea of bivariate random variable. Instead of describing an event using one number, you can use two number or actually even more. And by that, then we have to define the joint probability function, right? And we can easily define what's expectation of the sum and turn out that because linear property, we have sum of the expectations. That is not very surprising at all. What is more surprising, you have to keep in your mind is the variance of the sum, right? And in a very rare case where x and y are independent, there will be sum of the variance. And do note that this is not whole true. And in general, this is not right. And in general, it is the formula I written down here. The variance sum is sum of the variance plus two covariance. Okay. And this is very important because the covariance is measuring how things are related, right? You have to understand the structure of the portfolio, right? Then that implies there are some optimal mix goes on there. Okay. And today, the goal is to finish, at least finish all this, and we'll get to the continuous business. Okay. And probably ask why we want to study this five. And the reason is being that we are very general. We know the P is a description of random variable. And we want to know in application, what kind of P we will see? Do we have any structure to impose on the P? And in a lot of data application, there's some nice mathematical structure to impose on P that simplify our calculation, right? Because you can always go to the data will give the P, right? But we don't do that. Rather, we will try to see there will be simple we call the parametric family, where basically these kind of distribution can be described by several numbers, okay, that make our life easier. For example, the uniform is just saying that everyone is equally likely. There's nothing new there except the P's are 1 over n, right? And this is if this is a consecutive integers, then it's rather simple there, okay? And I guess we can go to a little bit more serious business is what we call binomial distribution, which essentially you classify the events are either success or failure, right? Just a binary wheel of the world in tomorrow is either success or failure. right? And success probability P, and failure is 1 minus P. And in this case, you only care about the number of success, right? So this table right here in the middle of the slide essentially give us the complete description of what we want, because the P is a complete description. I give this P is over, right? And you would know that there's a lot of application because, right, very often we just have a cutoff, right? Whether something is going to success or not, right? Is functioning or not functioning, right? So that is the idea. And as we said, P is rather complicated, and very often we would be focusing on the mean and the variance, right? As a summarizing what we know about P, right? And turn out the mean is just simply P, and the variance is P times 1 minus P, right? So that would be something we would want to know. And some of you may ask, right? We learned so many things in the topic 1, right? Including skewness and kurtosis, or IQR, or range. Are they going to be useful here? Yes. You can do all those things in this, do this to random variable, right? But our time is limited. We can't go over all those, but they are all used that also described in random variable. And if you look at Wikipedia or other encyclopedia, then you will see those. Okay. But for our purpose, a mean and variance is the main thing, right? Because you look at the investment, right? We will see the mean and variance, right? And of course, I also told in the first topic, kurtosis and skewness are also there. So you can also think of those as well. And after that, we talk about the binomial distribution, which said you repeat the binomial trial n times, and each time is independent. Okay. And I hope I remind you why we have NCX, right? And PX 1 minus PNX, right? Let me repeat why is the case. Again, because I guess after a while from your holiday, you forgot. Okay. So initially, you can have success or fail, right? In the binomial, the first one is binomial trial, right? It's P 1 minus P, right? Success means that there's one success, 0 success, right? Again, you can go again, right? Success, fail, and success, fail, right? This is P 1 minus P, P 1 minus P, right? And 2 success means number of success x equal to 2, right? And this means x equal to 1. And this is x equal to 1 as well, because failure success. And this is x equal to 0. Okay. And here you can see P of 2, which means that the number of success is 2. It's actually P squared, right? Because you just multiply along the edges. What about P equal to 1? It's going to be 2, P 1 minus P. Why 2 here? Because you have these 2 correspond to x equal to 1, right? And P0 is 1 minus P squared, right? And this would be holding in general to be true by the formula like this, right? This is the formula. If you write, it just P of x is equal to 2cx px 1 minus p 2 minus x. Why? Because this is independent, right? You can do the first round, okay? Is the first round successful? If x success is p times x, right? Because this is a multiplication rule, right? You find x success, each success has probability P is P times P times P until X times. That is the idea of multiplication rule, right? And then if on X success means 2 minus X success, so you times 1 minus P. Okay? But this is saying that the first X is success, the rest are not successful. But do remember that it depends on how you arrange the success, right? You can have first success and or second success, right? So there's 2 over X different way to reorder them. Why? Because you can imagine that you have 2 balls, right? If you draw no balls, no success. You draw ball number 1, first success. You draw ball number 2, second success. You draw both ball, both success. How many different ways to draw, right? It's 2CX. So this is the formula. If you don't like the 2, replace by N. That's the formula there. Again, I write that in the whiteboard. That means that you don't have to remember or you don't have to understand if you don't fully get it. But if you ever seen that again, then you will try to understand. I get that's what happened, right? You don't try to remember everybody you met, right? You only met them many times, then you become your friend to remember them, right? You don't remember everyone you saw every day today, right? So you just remember those people you know more, same as math. Okay. I try to introduce him to you. Okay. And if you like him, you understand him, that's okay. Right? That's good. You become friends. But if you don't like him that much, that's okay. You may see him tomorrow and then you may like him more, right? If you don't see him, it's okay not to know him. Okay. Because we are not asking you to derive anything, right? Just you know this formula, you how to apply, then that's okay. Okay. But I give you the idea what it is. Okay. And also if you want to know, it already gives you the technical slide here. Maybe you can ask AI, put the slide here up to upload the AI, then probably he can explain a little bit more than I do. But in any case, you can ask me or TA. Okay. And since the P is complicated, right? So that's why usually we care about the mean and the variance, right? But we still need the P to do all the calculation. But if you really just care about the mean and variance, which usually we care, we just MP and MP times 1 minus P. Do note that Y is N P times 1 minus P for variance. But for mean, it's very simple, right? Because you have N binomial trial. So the mean of the binomial is sum of N binomial, and the variance is basically variance of sum is sum of the variance, and this is independent, so that's why it's a sum. You don't have the covariance, okay? And because the sum is not n square, it's not n times one random variable, it's n independent variable add together, because each outcome is a binomial trial, okay? So that's why you see this formula there. Okay. If you get it, you get it. Don't get it, it's okay. So this is, you just need to have that in your printout when you go to the exam, right? If you do the assignment, you have that already. Okay. So this is a question about the application. I go over that again because that is a important way to understand it, because I said in the class again, green box is something you must understand in order to get good grade from this class, right? And also you will need to do it for the assignment, right? So even though you don't understand anything in the purple, green is the thing that we apply things in the practice. So how is this problem here? So a restaurant owner found 30% of his customer like spicy food, right? So that means that if you look at this question, if I draw a particular guy, right, then he would like this spicy food with 30%, right? And that means that he would not like, maybe that's not the, he would not like the spicy food with 70%, right? I join them guy, right? This is data, okay? Here we are coming from data to probability, okay? Do note there's a important jump between the two, okay? Because 5% is data, okay? But we are we are expecting the next customer should be following from data, okay? So here have a one important caveat here is data representative for the future, okay? If this is the case, we can apply this. If not, we don't. But in our class, we just assume this is going to be true. But in your application, have to be very careful. Is the data you have going to reflecting what to be seen in the future? You often seen in the investment fund advertising, the disclaimer, the past performance doesn't indicate the future, right? So have to be very careful. But we assume this is going to be true, right? So if I have a new customer comes in, the best guess for me would be 30% of time he will like spicy food. 70% of time is not. So that means that if I have 10% come in, 3 would like it, 7 would not. Okay, but I don't know which 3 with 7, right? That's probability idea. Okay. Now the question is asking the following: if I have 5 customer to be expected coming this morning, they book a table, and the question is, what is probably 2 of them would like spicy food, right? So the question of this is, how can you proceed, right? Of course, if you think about this, it is simply like a binomial distribution because each customer is randomly chosen, right? So basically, you are basically asking the question is you have 5 person here, okay? Okay. And how likely that out of 5, 2 of them is like spicy food, okay? The other 5 is not, right? So this is the question. Okay, so this is the question here. Okay. And do note that I put here in the order, but it can be any order, right? Here I put the first 2 likes it, the last piece is not, right? So for this particular order, okay, the first 2 likes it, the last piece doesn't. What's probability of this? It will be 0.3, 0.3, 0.7, 0.7, 0.7, right? Each one will come in this. And since they're independent, the multiplication rule, right, we will just multiply all together and that's it, right? So that's why it's 0.3 square, 0.7 cubic, right? So that is the idea. But you would ask why we have 5C2. The reason is this order can be anything, right? You can have the first 3 don't like it, the last 2 like it, these 2 can be in the middle, right? Can be anywhere. Then how many ways you can reorder them? Then basically you have 5 balls, you draw 2 balls, right? 5, that's 5C2, right? Or you don't like it, you can see this is just standard binomial, right? Because just have 5 boxes, right? You open the boxes there, each is a binomial trial. Out of that, 2, right? So that is P2 of the binomial. So it's 5C2. Okay? So this gives us the idea. Is that okay? This example. Now, let us continue with the little bit more advanced example. The same thing, but now is no more than 2. Okay? The previous question may not be applied directly, but this has business implication. Why? Imagine you're the owner of the store, and imagine that in your kitchen you have 2 portions of spice. Okay? The question now would be, do you need to reorder? Right? Because maybe order is there, but do you want to pay more for the faster shipping? Right? The question would be, depends on how likely that you run out of the spice, right? And if the probability is not very high, and then maybe you don't need to, right? And can do the same procedure before just the two, you can do 0 and 1, add up together. You look at the probability, it's 83%. Okay. Is it high or no? Your judgment. But maybe if I were them, I'm not going to take the risk, right? Because it's high enough probability that it's no more than 2%, right? That means that I'm safe. I don't need to order, right? That will be fine. I take the risk, right? Majority of the time, I don't run out of the space. That may be okay. Okay. So you can see this is a good application in business. Okay. Of course, this is not the only thing, because I don't think you only care about the spicy food in the restaurant, right? There are many applications as well. And there's a lot. Okay. I'm not going to go over every single detail, but I just highlight some, right? For example, you want to calculate how likely that in your shipment, right? How many products are defective, right? Because you do the warranty, then you need to ship how many products there, right? Or there are many things about the quality control, turnover, and also give, say, the marketing campaign, right? And maybe each call you're going to make is going to convert successful in a very low probability. And then you can see how many times you have to call to make a successful sale, right? Then you can see how many people you want to hire to do the telemarketing, right? So that is the idea. I'm not going to single detail for each single bullet point, because they apply the same concept we've seen. So you can take a look at your home, and then you will see this. And don't worry, you're given enough practice. When we finish this set of slides, you're given an assignment. Okay, you will do it, and then you know whether you don't know. Okay, because only by doing assignment, you know where you don't know. Because sitting here, it seems like, okay, everything seems to be very reasonable, logical following. I have no problem. But by only doing assignment, you will know. So you will be practicing, and then you can see this example makes sense or not. Okay. So I want to talk about the next. It's called the Poisson distribution. And this is very closely related to binomial. Okay. And in the sense that Poisson is just asking us to take the binomial n to infinity. Okay. So what do I mean by that? Okay. What I mean, take the infinity. Okay. Let me draw a picture. Okay. What are we doing binomial? Binomial with n, okay, and p, okay, is the following, right? You will have box number 1, box number 2, da 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 up to n. Okay. And you open one box, each box will have 2 outcomes, either fail or success with probability p, right? So they will be open a box, you have 2 outcomes, right? P is success. Maybe I use tick, right? If 1 minus p fail, same until the very last one, right? Same as we have 2 outcomes there. P is tick, 1 minus p is cross, right? And the binomial is asking in total how many ticks, right? So that is this is binomial. X is just number of tick, right? Number of success, right? So this is what we have, right? And it apply to many scenario, as long as you believe that the future is like this. And this is also in many cases has been used to describe stock market, right? Each box is a day, tick is the price goes up, cross is the price goes down. Okay, so that would be the idea. Or you can think of, you make a phone call, right? N phone call, P is the successful, you make the phone call and make a business there, okay? So on and so forth. Now, what do I mean by take N to infinity means that there will be many boxes, okay? As many as we want. Is that application that we have many boxes? Yes, we do. Imagine the following. Go back to the restaurant business analogy, okay? Or we have a time period of a restaurant, okay? And maybe the restaurant operate from 9 a.m. to 5 p.m. Okay. That is going to be 8 hours, right? 8 hours. Okay. Imagine this restaurant is in the middle of nowhere. Okay. That means that maybe a place is rarely visited. So you can imagine that they're lucky. They will have one customer in 1 hour. Okay. They very rarely visit restaurant. That means that you can think every hour. Okay. This like open a box, right? If one customer comes in, success, because this restaurant is rarely visit. Okay. And there will be probably P, one guy comes in for each 1 hour interval. Okay. And that means that this is a binomial distribution n equal to A, right? So maybe you can imagine P maybe half, right? Half of time you have a customer, half of time you don't, right? Every hour. So that would be a binomial. Okay. So, but imagine that this restaurant is getting more popular because of some KOL go there and take a picture. Okay, getting more popular. In that case, maybe the restaurant is getting more busy. It's not 1 hour you have one guy. Maybe you have half an hour you have one guy, right? That means that instead of this, you think about of the 8 hour divided into 16-hour interval, and each interval may have one customer, right? So the probability will be adjust, depends on how popular the restaurant is, but every half an hour you have one guy, okay? And this is still a binomial. No problem, I hope. Now, getting more and more people, you have more KOL and comes in, right? Getting even more popular. Maybe it's so popular that maybe you have every minute you have a guy, right? So it means that we have every minute we have this, right? You will have 30 minutes, right? Then instead of 8, 16, 30 minutes interval, you have 480 1-minute interval, right? And you can go on and cut this as small as possible, right? You go to infinity, okay? And of course, when you go to infinity, the P may be very small, right? But it's not zero, right? So that means that when n go to infinity, the special case of binomial, and this guy become Poisson, okay? And this is very good to model how many people arrive within a period of time. Okay, let me repeat. We can see what we are doing here is we are modeling how many people arrive within a period of time. Okay, and of course, the assumption here is like follow from binomial is how many people arrive here in each interval. It will be independent of here, right? If you say if there are more people in the morning, would affect how many people could see in the afternoon, then it doesn't satisfy the Poisson distribution. Okay, and if you want that, that will be more complicated. If you want to do that, you will learn this in advanced class in statistics, like you learn the Poisson process, those kind of stuff, much more advanced. But in our model, we assume that like because it's coming from binomial, so If you see a lot of people here, doesn't say anything about after. Okay. But this is the one of the very useful thing. Okay. So remember what we do is we take this binomial and take n to infinity. Okay. That means nothing new here for the Poisson, except for the fact that this is the same formula. But why we still call this Poisson? Because of the approximation in mathematics when n go to infinity, okay, and p is not big enough, okay, and this guy can be written as this formula, okay, we're getting this formula. You ask, okay, but why isn't this is better than this guy? Yes, but if you do calculation, you will see in this approximation is way much easier than this guy. If you learn any computer science, the reason is being that you have a NCX, you have 3 factorials, and factorial is super difficult to calculate. Okay, and there's some way to approximate. There's only 1 factorial, and the exponential is way easier to calculate. Okay, so that's why we have that. Okay, and you later see that there's also one very interesting property. So when n is large, p is small. Okay, that's very important, because when n is very big, p is very small, right? Because n is very big, p is the successful in the very small interval, right? So p is very small. So turn out that the one interesting is we no longer need to think n and p. We just keep the lambda. And the lambda is simply that how likely things would happen on average. And this NP is also same as the variance. Why? Because the P is very small. So 1 minus P is just 1. Okay. So in particular case, when you see your data, number of people would come, the mean and the variance are very similar, then Poisson is a good model. Okay. And there are so many applications of Poisson. I can't really list them one by one, but when you try to model how many people would come, right, within a certain period of time, Poisson is the first choice you would want to do. Let me give you an example. Okay. But before we do that, you will see the Poisson with a smaller lambda will be considered before, and the bigger lambda is more like spread out and more. And indeed, actually, you can show when lambda is large enough, that will be looks like a bell curve. We'll cover in the next class. So the bell curve is the standard thing you learn is a normal. The bell you learn in the high school is this. But anyway, we will not worry too much about this at the moment. Rather, I will point you to the example, okay, which I said Poisson is the way to model arrival of thing or how things happen over time. Here we have the example, again, the restaurant. And we said each hour, the arrival weight with the mean of 5. Okay. So already the question already start with assumption telling us Poisson. So here this example doesn't come from the data. We already told you it's from 5. But this is essentially same if I give you the question saying that on average, there are 5 customers in each period, then you can convert this information to the mean is 5. Okay. And now the question asks you is exactly 2 customers arrive in the next hour. Okay. That means that you would simply use the idea that this is a Poisson with lambda equal to 5. It's asking 2, right? So it's P of 2 given lambda equal to 5, right? So that would be the idea, okay? It's exactly this guy. And because the formula is E negative lambda to x factorial, so, right? So put lambda is 5, x is 2, so this, you get this formula, right? So there's only 0.084%, okay? Do note that the Poisson different from binomial, right? Because this is, binomial is, you can only have 0 up to n, right? And I said n go to infinity, right? So what kind of number you can have in Poisson is 0, 1, 2, up to infinity, okay? So then there's no limit on the Poisson, right? You can go as many as you want, right? So that is a good thing compared to binomial, right? Binomial, to know how many customer would come in the maximum, right? But now Poisson, you don't have to worry about that, right? You just need to know on average how many customer would come, then we're done, right? Is that okay? If you model a Poisson, you have to know how many customer might come in total, and then you calculate that, right? But here we don't have to worry about this. So it's even simpler model, right? Let me repeat. If you model the number of customer is binomial, then you have to come of the idea that potentially how many customer would come in hypothetical world, and what you actually see is the first box, right? It's going to be success or not, right? You have to come up with the modeling, how many in total potential to come, and then you can model the P, right? That you have to model two things, N and P. That is very complicated, right? But instead, you just need to know one thing, right? How many of people would come on average, right? And then you can just start, right? You don't have to model potentially how many of them might have come, right? So that is much easier problem. Okay. Is that okay? So probably you ask why we care about exactly 2 customer would come. Well, because you can also calculate how likely that you have 0 or 1 customer, right? And so on and so forth, right? You can ask those questions. If there are few customer would come today, probably you want to close your business, right? Or if there are many customer would come today, you may want to hire more part-times, right? Or you have many customer, do you think you need more food? So on and so forth. There are many questions related to operation that would require you to use probability calculations. And there are many applications as well, right? For example, you can calculate the website traffic, right? You can calculate how many people would come. Then you have to calculate how many bandwidth you have to do it, or how many computing power have to be reserved to serve the customer. So there's a many example here. I'm not going to one by one, but you can see there's a lot of application of Poisson. I'm not going to go into detail, okay, one by one. Okay. And then after the break, we'll talk about hypergeometric distribution. And you may ask, what is this guy? This guy is another case of binomial. Okay. In binomial, we open box one by one, and each box is independent. Okay. Opening one box doesn't tell me the next box. Okay. It fit very well when you have a very large sample, right? If I talk to one guy, okay, and I talk to the other guy, unlikely I met the same guy, right? Say, for example, I do a survey, right? Maybe ask in CHK, right? How many people like, I don't know, Mirror or 17 or whatever pop star you like, right? And the proportion is fixed, maybe 40% of the CHK student body would like it, right? That means that if I grab 10 people, then this is a binomial. That's okay, right? If I assume each box is independent. But what if it's not independent, right? Suppose in this room, right? I try to maybe out of 40 people here, right? Maybe 10 people like a particular pop star, right? But if I pick one guy, right, then probably I will not pick him again, right? So then I pick the other guy, right? In that case, each pick is dependent, right? Or you go to audit, right? You look at the warehouse, right? And if you check the inventory, you take out something and check it and put it back, you will not allow to do the same, pick the same thing, right? You're not allowed to check the same thing again, right? Then that means that you are not doing independent sampling, right? So each draw is not independent. So you have dependent draw, and that relate directly to our hypergeometric distribution. In the sense that, let me quickly, is you have n objects. Out of that, A of them are good. So imagine the good thing there, the bad thing there, right? And then you will draw n item there, okay? And out of which X are good. So let me draw a picture like this. And this after this picture, then I'll give you a break like this. You have n outcome here, right? You have number one, number two, number three, da 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 of n, okay? And I told you that number one to number A are good, and A plus one, maybe use other color, right? And A plus one, A plus two, da da da, up to n. These are all bad, okay? And these are all good, okay? Okay. And the question, of course, you don't know which one are good or bad, but you are going to pick up, in the case, because you're doing some sampling, you're going to take n guy out, okay? The question is, out of n, what is the probability that X of them is good? Okay. Maybe saying you pick up 10 object there, what is probably two of them is good? So you would often do this in your uh, auditing, quality control, or sampling without replacement. These are rather standard. Don't worry, we'll talk about this during the break, after the break. Okay. So, uh, if you have time, please fill in the U reply, and then we will resume after 50 minutes. And since next Monday is our Mid-Autumn Festival, so I bring you some small gift and to enjoy during the break. So we'll doing hypergeometric distribution now. There's still more. If you want to celebrate more, you can just free to come to take. So let's get back to business. I hope you have a good break. So the question is, can you use the calculator to put lamb, the question mark, and professions? Oh, so you can bring your calculator to the exam theater, and I would say my class is not intended to ask calculation. Okay. So you shouldn't expect, I mean, assignment, of course, ask more calculation, but the exam, you are not expected to do a lot of elaborate calculation. Okay. So most likely you are doing the division, addition, multiplication, the standard thing you learn in the primary school that will be most calculation we will need. Of course, we're also checking some tables, but that would be the thing we're asking. Okay. Uh, but maybe exponential, say Poisson, maybe I need, but usually I will not. I'm not a big fan of asking those, right? But at the worst case, if you forget your calculator, you show your intermediate step, right? It's correct. You didn't have a final answer. Maybe we just take out a very small part of that. Okay. So make sure that you write intermediate step so that we can give you as much as we can. Okay. So that would be something I can say. So difficult. I said nothing. So I recommend you to watch our video again or ask the AI, which hopefully is going to help. Or if not, then you can ask our TA. Okay. Please schedule a meeting with TA if you don't understand, because it's very important to know what you're doing. Otherwise, I mean, what's the point, right? Because you are a full-time student, right? Suppose you should spend at least 8 hours into a study. You ask yourself, do you spend 8 hours for your study? If not, then you are not a right responsible students, right? So you should, I mean, for each class, right, you are expected to spend 3 or 4 hours per week for each course, right? Depending on the credit, right? We have 4 credit class, so spend 4 hours. But in our class, right, I don't think you need to spend more than half an hour each week, right? If you don't have assignment. So, but anyway, do schedule appointment with TA if you don't understand. Okay, she will try to help you. Okay. Of course, if she can't help you, I will try to help. Uh, but if you just write this, I really can't help. So please write down actually what you don't know. Otherwise, I really don't know where you don't know, right? And if you don't know, as I said already, we have a self-checking quiz. Okay, please go to the self-checking quiz and do it, and there's answer there, right? So if you are okay with the self-checking quiz, then basically, I'm pretty sure, I mean, more or less you should be able to get an A or A minus from this class. Okay, because I don't think my exam is more difficult than the quiz. Okay, it will be the same level or even easier. Okay, same as assignment, right? Our assignment is pitched at a higher level than the exam, so the exam will be asking a slightly lower level. So as long as you think you can do the assignment, you can do the quiz, I don't think you have any problem with your final exam. Okay, so its class is not a difficult class. Of course, we have a lot of material. Okay, but it's not something very difficult. Uh yes, a new hairstyle. I guess you are meaning me, right? It's a new hairstyle. Yes. Um, yeah, because we have holiday, so we have something to celebrate. If you want more, yes, feel free to get if you are hungry. So at least I'm useful, not at least in terms of study, at least make your stomach not so hungry. Yeah. When is midterm? Let me repeat again. There is no midterm for our section. Okay. No midterm. Okay. We already have quizzes. Okay. The quizzes serve the purpose of midterm, but it's self-checking. So as long as you do it, you get full credit. So if you don't have to make it full, so as long as you do it at the end of the semester, you're done. Okay. And also remember, we're lucky that our class have another tutor who will be holding tutorial section as well. Okay, so in the case that you don't know, please attend those optional tutorial. Well, I think we'll announce later this month. We have one tutorial during the midterm time. Okay, and one tutorial before the exam. Okay. Sleepy every day. My recommendation: very strong coffee. That's what I did in the morning. um, well, I would say if I like you, as young as you, I would drink coffee with milk. That would make easier. But if you are so busy, so tired, you drink black coffee because actually your tongue you feel numb. Only black coffee you can taste something. So and I probably I mentioned again, right? There's an old TVB dialogue, right? Real man or woman drink black coffee. Okay. And only when you appreciate what is the black coffee, you think it's good taste, then you become mature. Okay. That is I think I don't understand when I was a kid or young, but now I understand. When you really appreciate the black coffee, then you really understand the meaning of life. Okay. I mean, many people in MTL, yeah, that's true. Um, the day of midterm, there's no midterm again. Days of final, I said already, is November 29th, right? Um, I think the TA has already announced it in the blackboard. Uh, sorry, November 27th. I mean, I think she already announced it, right? Um, but didn't put it there. Um, oh, I guess the reason she didn't put it here because of the venue has not been fully confirmed yet, but it will be the it will be November 27th. Uh, it will be I think 6:30 to 7:30, and that's it. The 1 hour, just 1 hour, 1 hour on exam. But she will announce once we confirm the venue. I think it will be 里達三樓 on the near after the library, but we have to confirm that thing first. But it will be just 1 hour. What's it 1 hour? Okay. Of course, if you want more than 1 hour, let me know. But I guess 1 hour in the past has been sufficient to do everything there. Okay. Um. Okay, that will be the final. I think the final will be released to you soon. Okay, the day. But I think I will announce that. But if you have legitimate reason cannot attend, please email the proof to the TA. The TA will organize another centralized makeup exam if you happen need the makeup. Okay. Uh, and if you can't do the second centralized makeup, then we'll do individual. Okay. So you have, but you then the makeup, you have to have the proof why you can't do it. Okay. Otherwise, I assume you do uh the biggest exam. Oh, lucky today. We have everyone know what day is today. Okay. Friday. Okay. Weather, yes, nice weather. Um, yes, Poisson is very useful thing. Um, so let me repeat. In our class, that essentially there's no stat until now, right? Basic sum probability. Okay, stat is actually next week, from next week onward. There's actually no stat, and even for our stat, it just we are learning some very elementary thing. It's not really a stat. I would not call it stat, but you may call it stat. But I don't think we're really doing anything stat. But we're just learning some idea behind stat. Okay. But well, I haven't even covered that, so you learn it already. That's nice. So you learn ahead. So everyone seems to be fine. The speed seems to be okay. Uh, most of you can follow. I'm happy for that. The deadline of self-checking quiz is the end of semester. I will just check if you have done it. You done it. You got full credit for the part. Okay, no deadline. I mean, as I said, just attempt. Okay, as long as click in and submit, then you get the grade already. Okay, there's no need to worry about. And if you think it's too much, you don't have to do all the questions. Okay, remember, you just need to attempt some of the questions, then you're done. Okay. A guy went into a hotel. Sorry, there's no room available at the moment. My name is Improvement. There is room for improvement. Okay, that's good. I'm on diet. Okay, so that's good. Dog. Oh, I think this guy used Twitter. This is what the Elon Musk today's tweet. Only one thing, full stop. I think someone is following Elon Musk. Wow, very long. Wow. Eating banana, whatever. How is surviving? Maybe we don't have time to go over a very super long reading. I'm sorry that I skipped for this time. Um, okay, that's a good one. If you see okay, if you, it's good. No jokes today. Today very hard. Um, I'm sorry you're confused, but do let me know what you're confused so that I can pinpoint and help you. But let me repeat, please look for TA if you're confused, and she will help you. Okay? Definitely look for TA. You pay for that, okay? Your tuition include our TA fee. So please do look for TA. If TA also said sometimes she's very bored because no one is trying to talk to her, right? Please help our TA make her life more fun. Okay. If you are confused, you don't know, please look for TA. Okay. Of course, I'm also willing to help you, but you have to write down here. Otherwise, I don't know. Okay. I can't really go for one-to-one. Okay. Um, so let's continue. Our hypergeometric. Okay. And remember our slide over here, right? So binomial is opening n boxes. Each box opening is independent, and each box opening you have two outcomes: success with probability P, fail 1 minus P. And Poisson is asking actually you open infinite many box, right? And each box has probability P, right? But we don't use NP concept. Rather, we use within a period the lambda of people would come, right? And that would be in overall period, an expectation lambda people come, right? That would be the idea here. And hypergeometric is very related to open and box, right? But rather, it's not each box independent. You're actually drawing something directly. So here we have n, big N different objects. Okay. Out of A, we call success, right? Maybe you can say n object out of A are good thing. Okay. A plus 1 up to n are defective items. Okay. And you're going to see, draw small n out of this. Okay. And then you ask how many of them is good, how many of them is bad. Okay. If you draw it and put it back, that's binomial, right? You draw it and you cannot draw again, that's hypergeometric. Okay. That's a difference, right? Because if you draw it, okay, how likely you get good thing is just very simple, right? It's just A over N, right? If you draw only once, right? You don't put it back, right? How likely you get object in the red? A over N, right? Okay. So it turned out that, and then if you draw two objects, okay, in the binomial idea, right, it's just 2 times over n, right? So that's why turn out that if you draw it, okay, and put it back, don't put it back, right? You draw it, don't put it back, the expected value is still same as NP, which is NA over N. Okay. This is something very interesting. Okay. You draw it, but don't put it back. In terms of expectation, it's same as to put it back. Surprising. Okay. We're surprising. Okay. Right. Because we're surprising, right? If each one is independent and each one is dependent, the number of successful the same. Okay. Get the idea, right? So suppose I draw n object there, right? I draw many of them there, right? Put it back or don't put it back. How many of them are going to be successful? In terms of expectation, they're the same. Okay. And in terms of the variance, it is slightly different. Turn out to be is NP1 minus P, but you have another term, which is N over N minus 1. Okay, this is in your slide already, so don't worry about this on your slide. So this part is same as binomial, but this part, which is less than 1, is not binomial. Okay. You may ask why the variance is less than binomial. The answer is very simple. If you draw and draw and draw, what's left there is less and less, right? So suppose you draw everything, then, right, there's no variation because you draw everything every time the same thing, right? So which means that your variance will be decreasing in your small n, right? You draw more items. So that's why this part has to be smaller, because when you draw the thing, don't put it back, the variation less, right? When you draw more and more, there's less thing left, right? When you have very little thing left, then there's not much variation. So that's why this is what we call the finite sample correction. So it's a smaller, it is less than 1, right? And of course, this is only the mean variance, right? So the question is, what is P of X, right? What's P of X? Okay. And this is not difficult. This is just the idea coming from combination. Why? You are drawing an object of n, right? So that's why this is how many possible things you can draw, right? You have big N number of balls, right? You draw small n, right? So that's how many ways you can draw it. Okay. And remember, principle of counting, you have to draw success and fail, right? So how many things you can draw from the red one is A of X, right? This is only the way that you can have success. Okay. And how many that is not is from the blue is N minus A. Out of it, you want N minus X, right? This is how many ways you can have red, how many things you have blue, how many ways you forget about the color, right? So this is the probability. So this is hypergeometric. Is that clear? Of course, I wrote it in the whiteboard, means that if you get it, you get it. You don't get it, it's okay. Don't worry too much. Okay? Okay? Whenever I put it there, right? You don't have to worry about that. Okay? Yeah, otherwise, I should have put it in slide, right? Everything in the slide, the green color and the purple color, you should remember, especially the green, right? The purple is good to bring it to your exam theater, right? But the white thing, if you get it, it's okay. You don't get it, don't worry too much. Of course, if you're curious, you can ask me or ask the TA or watch the video again. Okay? Now, let's get back to our serious business. Okay? That's why we're here. This is the formula. Okay? So to convince you, when I was a student, I learned many statistics class. I don't get it in the first time. So it's okay to not to understand it. Okay? I have to say I'm a student who do actuarial science, which basically the major is doing statistics. I do more, basically my undergrad is basically statistics. Okay. So I learned so many classes And then I learned a lot of time and took the exams. Then after many, many time, I understand this. Okay. It took me a long time to understand. So I don't expect you to learn in my class once and for all. Okay. If you see it again, then you think about it more, then you understand. Okay. It's not easy to understand this. Okay. So, but it's okay. You just need to know the P function. When you see this hypergeometric, it's like this. Okay. The only thing to remember when you use this thing, right? Because we are business school student, we need to know how to apply, right? The details can be learned later, right? You know how to use it, okay? Just like the analog, right? Your phone, do you know everything, how the phone works? No. You just need to know how to do the app, right? You don't need to know how to program the app, right? It's the same idea. Just the first thing to learn is how to use it. Okay. So here is the formula I've already showed you. This is the mean. This is P. This is 1 minus N P, 1 minus P, adjustment term. Okay, so I already told you already. Okay, so this is what I said in the whiteboard. There. Okay, so hypergeometric. And later you will see, not clearly enough now, but at least when N is big, okay, this is close to the bell curve. Okay, so you can later you will show is whenever you have a large sample, always you can go to bell curve, right? But when data is not big enough, then bell curve doesn't work very well. So you can go back to this kind of precise definition. Okay. Now there's many. Then I want to give example to illustrate how hypergeometric distribution is being used. Okay. In our class, we will tell you that in this scenario, what distribution to be used. Okay. But this for our class. In your application, in your future daily life, you have to decide which one fit, which one doesn't. Okay. It's not my job to tell you. Okay. But in a class, I tell you. But in the real world, either your boss tell you, right? Or you try to decide which one would fit. Okay. But in this case, would fit very well because you go to audit. Okay. There's a warehouse and 4 of them are defective. Okay. And then the question is, you're going to take 6 out of them. Okay. And how likely 2 of them are bad. Okay. The question is like this, right? Just to imagine the following, right? You have computer number 1, 2, 3, 4, a bad computer, right? And computer 5, 6, up to 30 are good computers. Okay. The question is, you close your eye and draw 6 of them because you don't know which one, right? It can be anything there, right? You're going to pick up, I don't know, 6 out of them, right? Right? I think I draw one more, right? Something like that, right? This is 6, right? So you draw 6. How likely this or similar would happen, right? You draw 2 red and 4 blue. Okay, this is what you're asking. And because why this is a hypergeometric, not binomial, is because once you take out the computer, you check it, you don't have chance to check the same computer again, right? We know it. We put, say, once I check it, I put aside, this is a bad computer, and I'm done, right? I'm not going to put it back. If I put it back, that's binomial, right? But if I don't put it back, right? I remember this computer, I don't draw it again. That is hypergeometric. Is that clear with the difference? If I take the computer, I check it, I put it back, I forget about it. I may be drawing it again, then it's binomial, right? But if I take it out, I check it, I put a sticker on it, okay? Then I'm not going to draw it again, then it will be hypergeometric. So this is very simple, right? When you do audit, it's always hypergeometric because you can't check it again, right? But of course, if I check it, the other guy come in to check, every day have different auditor, right? You allow things to happen at the same time, right? Then same thing can be checked, right, over the days, then it will be binomial, right? It really depends on the process you are thinking in your mind. Okay? So we know hypergeometric, that's very simple, right? That is P of X is simply big N, Cn, Ax, N minus A, right? N minus X, right? And you just know 34, 6, and 2. That's you put it in and you have the answer. Okay? So that is the case. Okay? And of course, you would worry about you put this in your Excel, it's very complicated, right? But at the end of this set of slide, there's one line Excel code will give you immediately with this. Okay? So you don't have to worry about too much about this calculation. Okay? But I just have to show you how you get it from scratch, right? But Excel can tell you once you input N, A, N, X, then you're done. Okay? If you are impatient, you can run over your slide to the very last few pages. You can see that. Okay? But I'm not going to talk about this until we talk about Excel. Okay? Is that okay? Okay? If that is no problem, then you can see a lot of example, right? Especially in audit, in quality check, right? Because a lot of quality check has to be destructive tests, right? For example, right? You want to see if a drink is drinkable, you have to open it and drink it, right? Once you drink, you destroy the product, right? So that means that it must be sample without replacement, right? You can't just put it back, right? Once you drink it, right? I test it, I put it back to sell, right? You can't do it, right? So you can't really do that part. So that means that have to be that case. Is that a question? No, then we're done with discrete. Okay, we're done with discrete. We're happily, we go to continuous. Okay. Continuous random variable. Okay. So the first thing is how do you model this, right? P of X. So first is continuous random variable. You can't have P, unfortunately. I'll show you why. Because P is 0 everywhere. Okay. For example, you try to pick a number, a decimal number from 0 to 1. Okay. And how many number between 0 to 1? Infinite many, right? As many as you want. So there's no number you can put probability. If you put it, add them up, it becomes infinity, right? No matter how small you put. So that means that we can't have that. So that's why, as I hinted, you can't use spec P. You have to use spec F. I will illustrate an example. Okay? Suppose you focus on the simplest case, uniform distribution, okay, over integers. Okay? If you have 0 and 1, equally likely, this is the P, and the F is just stacking. Okay? Nothing new there. Okay? And if you have 0, 1, 2, each one's equally likely with probably 1/3. Okay? And you stack it up, this is F. You can imagine that you have 4, the same, 5, the same. This is always this 45-degree line, right? It's go up there, right? But this, the height will drop. If you have 4, you have 1/4. 5, 6, 7, 8, 9, 10, right? If this is super large, this is 1/n super small. When this go to infinity, 0 everywhere. Okay? So that means that is P means nothing in continuous because any number is 0. Right? Just like the problem like this. Look at my head, right? I still have some hair, right? I'm not a monk, right? So still have some hair. Not old enough to no hair left, right? So maybe you it's better for take your hair. But anyway, look at my hair. I pick a particular one, right? And how likely I'm going to pick the same one? Not very likely, right? If I have more hair, then basically zero probability, right? The same idea, right? How likely you met the same hair, right? So if you have, that's why the monk or the Buddhist said, right? How likely you met your romantic partner, right? How likely? Very little, right? You take 300 years of work to meet your partner, right? So that is what they said, right? So it's very low probability you met the same person again. So same as your classmate. So, right? How likely you have in this class? We're unlikely, right? So it's lucky that we are meeting each other. But anyway, so look at the big F. Okay. So we can use P, but F is still meaningful, right? Remember, right? We still have the upper sloping F. So F, the definition we're the same, is the probability that the random variable equal to that number or less. Okay. And as we said, okay, P is zero everywhere, right? And we can say the probability between A and B, right, is FB minus FA. And larger than B is 1 minus FB, right? This is complement rule. This is just what we call the total probability rule, right? Because it's less than or equal to, it's less than, so they add up together. Okay. Now, although we say P is not defined, we can define something like P. Okay. Not always defined, but in our application, for your application, it would always define. So this is what we call the probability distribution function or probability density function PDF. So what's that? Okay. This is the idea that the probability within two numbers is simply given by the area under the F function. Okay. This is same as the idea of this. The bar chart, the height is the probability. Okay. Now we look at area. So let me give example to be a little bit more straightforward. So we'll create a function called F. Okay. Okay. And look at the number A here. You calculate the area. Okay. The area under this curve F will be the probability. Okay. So F, this area blue, will be equal to FA because FA is the random variable that is equal to less than that number. Right? F of A is probability that equal to less than A. Right? And if you go the right hand side from A, it's 1 minus FA, right? Because that's probability that random variable is more than or equal to A. Right? And if you look at F, the area between A and B is the probability between A and B. Okay? So that's F. Okay? And you would ask, is this function always exist? Okay? If you learn calculus, this is only doable when F is differentiable. Okay? But we're not talking about calculus anyway. Okay? But in our application, it's always doable. Okay? It need not be doable. Okay? And only differentiable and very nice property you can have that. Okay? Okay? If you learn calculus, F is defined in this way. Okay? Just X is looking at the random variables X plus a small number divided by that. So that's why if you learn physics, this is called density. So that's why it's called probability density function. Okay. And if you really learn calculus, the small f is the derivative of the big F. Or the big F is the integral of the small f. Okay. If you don't learn calculus, you can forget about this line. Okay. But if you know, you know. You don't know, you don't know, right? So forget about it. But I just say it because if you go to learn higher level probability, you can't escape integration or differentiation. Okay. But I just keep that there. In case you study in the future, I think 99% of you would not. So, but I just keep it in case you really want to do it. You can check it back. Okay. And one thing I have to mention now is what we call the inverse of F. That is a little bit important because we use it all the time very soon next week. So let's talk about this F function, right? This F function is the CDF, right? The cumulative distribution must be increasing, right? Because it cannot be decreasing, right? So it would be look like something like this. Okay. Remember, at most is 1, right? Cannot be more than 1, right? 1 is its upper bound, right? And this is a increasing function. If you learn math, okay, you will know the inverse would exist. Okay. But let me first talk about what the function is, right? Remember, if I have a number here, x, okay, you go up and check this f of x, right? You go this way, right? You give me a number, right? Look at this graph. This will give me the probability that the random variable less or equal to that number, right? And the inverse is the following. You give me a number y here. Maybe there's other color. You get number y here. You go the other way around. Okay. Then this is f inverse of y. Okay. It's going back. And this is always exists because f is increasing function, always go up. So it always exists an inverse. You can always find, you can just go back and forth. Okay. So this exists. And later you will see this go back will be very important for our purpose. Okay. So, and if you don't want to look at this f inverse, what we are doing is the following. Remember, we have a f function here, right? The f function is, for example, is as this, right? The probability, suppose this is the a, right? And this part is f of a, right? Right? So this, the area is f of a, right? So I give the number a, and you can tell me the area, right? This is f of a. But very often, we do the opposite case, is we will have an f here. Sorry. Okay. I give you this area. Okay. I tell you what the number is. You want to give me this number. Okay. From the area to a number is the inverse function is doing. Okay. I give the area on the left. You tell me what the number is here. Okay. Is that clear? Of course, they're the same thing. Okay. The same thing. Is that okay? Is that okay? Is that okay? This is the idea. So last minute, I would just want to say one thing. Since we don't do integral or differentiation, I'm not going to define what's expectation or variance. But the idea is the same. You do this experiment many, many times. You convert the outcome to the numbers and look at all the number there. Average of this number is expectation. Okay. You calculate the variance of those number is the variance. Okay. For those who like calculus, this is the formula. Okay. But we don't require that. Okay. Just have fun. Okay. And next week, we'll go over all this thing. Okay. Enjoy your holidays and happy mid-autumn.